Let's take a look at this problem. This is 837. We had started it in class and finished it very quickly, so I wanted to go through this perhaps a bit more slowly and make sure you understood this ideal regenerative Rankine cycle. So 8.37, the problem statement says, water is working fluid in an ideal regenerative Rankine cycle. Superheated vapor enters the turbine at 10 megapascals at 480 degrees C, and the condenser pressure is 6 kPa. Steam expands through the first stage turbine to 0.7 megapascals, where some is sent to an open feedwater heater at 0.7 megapascals, the same pressure. The remaining steam expands to 6 kPa, 6 kilopascals, for the condenser. Saturated liquid exits the feedwater heater at 0.7 megapascals, and we want to determine Q in, the thermal efficiency, and Q out. Okay, so I've highlighted those on the right-hand side. We went through the derivation, how to determine these enthalpies in class. If you're unsure how to do this, either come see me or take a look at the next video that I'll be posting where I work through how we can determine the enthalpies at each one of these states explicitly. Why do we look for the enthalpies? Because each one of these components we recognize as an open flow component, and it's the change in enthalpies that dictate how much work is produced or required by the component, or how much heat is transferred into or out of the component as necessary. So it's the enthalpies that dictate this. So if we can determine the enthalpies at each one of these states, then we can measure the performance of this regenerative ideal Rankine cycle. Okay? This one has an open feedwater heater, so one of the first things that we've learned that's a bit different about this cycle is that we actually split the mass flow rate, in this case, into two different legs of our system. One portion goes directly into the open feedwater heater at 7 bar, or 0.7 megapascals, and the other leg goes directly into the condenser at a lower pressure at 6 kPa. Okay, so that value Y is a mass fraction, and it's a value that ranges from 0 to 1, and it basically says how much, in terms of mass, are we siphoning off between these two legs. Okay, so Y might be a value, say, 25% or 0.25. Then, of course, 1 minus Y would be the remaining percentage. That would be 75% or 0.75. And it just gives us an idea, a number that we can associate to the total mass flow rate and say, what's the percentage that flows directly to the open feedwater heater? What's the percentage that flows directly into the condenser? The usefulness of our open feedwater heater is because we know that our thermal efficiency is dependent on the net work, but also dependent on Q in. So if we want to increase our thermal efficiency, the thermal efficiency of our given cycle, then we can either increase the amount of work that's produced, or we can decrease the amount of heat that's required to go into our system. By siphoning off a portion of that mass flow rate directly into the open feedwater heater, what we're doing is we're taking some of the workload off of our steam generator to heat up our working fluid from that small gap from state 5 to state 6. Okay, so now Q in only occurs from 7 to 1, not all the way down from state 5 all the way up to state 1. So by reducing the Q in workload, we've increased our thermal efficiency. Now you might ask yourself, well, doesn't that also require us to add in another pump? And by adding in another pump, doesn't that decrease the amount of net work? Well, it's true, net work does take a little bit of a hit, but it turns out that the increase, or rather the decrease in Q in, the added value of decreasing Q in outweighs the additional amount of work that's required to operate that second pump. Look here, we have one pump from the condenser, and we have a second pump downstream of our open feedwater heater. Okay, so we now have two pumps, whereas before in our just simple Rankine cycle, we only had one. Okay, but what we find out is that the benefits of reducing Q in outweigh the penalty of introducing that second pump. So we'll see that in just a little bit. So the first thing we want to find is simply Q in. And as I just said, Q in now only occurs, well, always only occurs, in our steam generator, which is between states 7 and states 1 on our diagram, okay, which correspond to state 7 and state 1 on our TS diagram. Okay. So Q in, we can simply solve for that immediately by just recognizing that it's the change in the enthalpies, H1 minus H7. We've already solved for the enthalpies, so we can just plug those values right in. 3321.4 minus 707.52. These are both in kilojoules per kilogram, so we're adding apples and apples together. This turns out to be 2613.9 kilojoule per kilogram. Great. We've just solved our first part of the problem, was to solve for Q in. But we also need to solve for for our thermal efficiency, eta TH. Okay, so our thermal efficiency, as I wrote down just a second ago, and I circle it now, is dependent on the net work that's produced by your cycle with respect to the amount of heat that you've put into your cycle, Q in. We just solved for Q in. That was the first part of this problem. So therefore, we need to solve for the net amount of work that's produced in this cycle. Okay, so if I take my marker here, and I recognize that the work in is equal to, the net amount of work is just simply the work that's produced by the turbines, the work out, which is produced by the turbines, minus the work in, and this would be the work that's required to operate our pumps. Okay? So in order to solve for W net, which goes into our thermal efficiency equation, I need to determine how much work is produced by our turbines, how much work is produced by our pumps. So let's take a look at our turbines. Let's write the first law of thermodynamics. We have this memorized. This is an open system. It passes through the turbine, so we have mass passing through the turbine. dE dt is equal to Q dot minus W dot plus summation over all the inlets, M dot HI minus the summation over all the exits, M dot H exit. Okay. Now, to be absolutely clear, I could put the E's and the I's next to my mass flow rates, which is probably more complete. I've disregarded my change in kinetic energy. I've disregarded my change in potential energy because these are negligible factors across a turbine. What also is negligible, or actually just goes right to zero, is dE dt. We're in steady state, so there's no energy accumulated within the boundary of our system. In this case, we're talking about the turbines. There's no energy that's just sort of building up inside the turbine itself. It's just steady state. Okay? There's no heat transfer through our turbines as well. We assume that it's adiabatic, meaning that there's no heat transfer. When I solve for work dot, or W dot, is equal to the summation of all the inlets, M dot IHI, minus summation over all of the exits, M dot EHE. Okay. Well, let's take a look at our diagram again. Now, our turbines accepts at the inlet, state 1, the total mass flow rate, which we can just leave as a general term, call it M dot. However, the exits, there's two outlets to our turbine. There's one at state 2, right here, and there's one at state 3. And the total mass flow rate combined goes through both of these states. But state 2 accepts a portion of the total mass flow rate. State 3 accepts another portion of the total mass flow rate, which is dictated by that quantity Y that we talked about before, that mass flow rate. So this is a value, again, Y, ranges from 0 to 1, and it describes the percentage of the total mass flow rate that goes through that leg, which enters directly into the open feedwater heater. The remaining portion is the portion of the mass flow rate that goes directly into our condenser. So if we go back to our first law equation that we wrote for the turbine, we recognize that W dot is equal to, well, there's only one inlet. It's the total mass flow rate times the enthalpy at the inlet, which is state 1, according to our diagram, minus the mass flow rate exiting at each one of those outlets. So at state 2 sees a fraction of the total mass flow rate, called Ym dot, times its enthalpy at state 2. State 3 sees a small fraction of the total mass flow rate, the remaining fraction of the total mass flow rate, minus 1 minus Ym dot H3. Okay. Well, we have a couple unknowns here. We don't know the mass flow rate. We don't know the work produced. That's what we're trying to look for. That's W dot. We also don't know what Y is. Okay? So we're going to come across this problem every time we solve a Rankine cycle with an open or a closed feed water heater, because you're siphoning off a portion of the mass flow rate. In order to solve this problem, well, first of all, we can simplify this slightly by dividing both sides by M dot. What we get is W dot over M dot. If we were to just simplify this, this is just going to be equal to lowercase w, not the net work. No, this is the net work. This is the total amount of work out by the turbines. Is going to be equal to what? It's going to be equal to H1 minus YH2 minus 1 minus YH3. So in order to solve for the work of the turbines out, we need to determine what Y is, that mass fraction that enters into the open feed water heater through state 2. In order to do that, let's consider the open feed water heater as our system and draw out the first law of thermodynamics for our open feed water heater. Open feed water heater has two inlets. One is at state 2. The other inlet, if we go back to our diagram, is state 5, and the exit is state 6. 5 was the inlet, 6 was the outlet. First law, dE dt is equal to Q dot minus W dot plus all the inlets, M dot IHI minus the summation over all the exits, M dot EHE. Again, we disregard kinetic energy and potential energy because it's negligible in an open feed water system. We're in steady state, so dE dt goes to 0. There's no stray heat loss in an open feed water heater. All the heat exchange occurs internal to the system boundaries, and there's no work being done on the boundaries or accepted by the surroundings on the open feed water heater itself. So what we get is 0 is equal to M dot Y H2 plus M dot 1 minus Y H5 minus M dot H6. Now, how come we had to factor in these Y's and 1 minus Y's that appear here and here? Well, it all comes back down to our diagram. We've siphoned off at states 2 and state 3 a fraction of the total mass flow rate. So whatever passes through state 2 from the outlet of the turbine, that mass flow rate must remain constant until it enters the open feed water heater here. Same thing goes for state 3. It passes through the condenser. The mass flow rate remains constant, passes through the pump, comes up here through state 5. So this entire leg only sees the fraction of the mass flow rate equal to 1 minus Y. The mass flow rate entering at state 2 must still be Y. And of course, because the mass flow rates combine in our open feed water heater and then leave, and we're in steady state, then we must recover the total mass flow rate, or y is equal to 1, at the outlet at 6. So that's why I have to include those terms y in this equation here. Now recognize that we know H2, we know H5, and we know H6. Also recognize that m dot appears in each one of these terms, so we never even need to solve for the total mass flow rate because it divides out because this equation is equal to 0. I'll leave the algebra up to you. Y turns out to be, when I do this, 0.2152. Now what does this represent? It means that 21.5% of the mass that enters the turbine at any given moment is going to be siphoned off and passed directly into our open feed water heater. That means about 75%, the remaining mass fraction, goes directly into the condenser. That's what Y actually represents. The mass fraction that enters the open feed water heater, the remaining goes right into the turbine. Again, why did we need to solve for Y? Because way back here, when we wanted to solve for the net work, which goes into our thermal efficiency equation, we need to determine the total amount of work that's done by the turbine. And because the turbine work is dependent on Y, we needed to solve for Y. So this equation, feel free to rewind this if you need to remember why we or how we developed this. But this equation explains the total amount of work out on a per kilogram basis by the turbines. It's in terms of enthalpies that we know, and now that we've solved for Y, that mass fraction, we can solve for the work out from the turbines. This turns out to be 1166.34 kilojoule per kilogram. I strongly recommend that you actually punch these values into your calculator and start practicing calculating these values. Okay, this turns out to be 1166.34. Check me on that. We're motivated to solve for net work because the problem asks us to determine the thermal efficiency. In order to determine net work, we also need to determine pumps in. We just solve for the total amount of work out by the turbines. So in order to determine the amount of work in for the pumps, we turn to our friendly equation, the first law, which we've used extensively so far in this exercise. dE dt is equal to Q dot minus W dot plus the summation over all the inlets of M dot I HI minus the summation over all the outlets or exits, M dot EH E. We're talking about a pump here that's in steady state. dE dt goes to 0. There's no heat exchange with the surroundings. That goes to 0. And we're left with W dot. Bring this over to the other side for the pump is equal to, well, let's go back here to our diagram. How do we determine the total amount of work that's required to operate the pumps? Oh, we have two pumps, don't we? We have one pump that transitions the working fluid from state 4 to state 5, and a second pump across state 6 to state 7. So we need to include both of these pumps into the total amount of work in. Okay? So actually going back here, we recognize, whether we use the diagram or the TS diagram, I want to erase some of this so that it doesn't get too sloppy, but we recognize that 1 minus y, that mass fraction actually passes from 3 to 4, right? When we look at our diagram that we've drawn to the right, that green arrow that squiggles its way through the condenser and through pump 1, the mass fraction, 1 minus y times m dot, represents the total amount of mass flow rate through our condenser, 1 minus y. So that means that the mass flow rate from state 4 to state 5 is m dot times 1 minus y. Cross 6 and 7, this occurs downstream of the open feed water heater, and we said that at state 6, the mass flow rate is the total mass flow rate from state 6 to state 7. So when we draw out our first law for our pumps, W dot for the pumps, we want to include the fact that we have M dot times all of the inlets. We have an inlet at 4. H4 minus H5. But we only have a small fraction of the mass, total mass fraction that passes through there. So we need to include that 1 minus Y term in there as well. Plus the total mass flow rate that passes from state 6 to state 7. H6 is the inlet minus H7. W dot over M dot is equal to lowercase w for the pumps. That's going to be equal to 1 minus Y, H4 minus H5, that whole quantity, forget the brackets there, plus H6 minus H7. H4 is less than H5. H6 is less than H7. H4 is less than H5. H6 is less than H7. So this will be a negative value. So if we define the amount of work required by the pumps and call in positive in this case so that we can remain positive people, we can solve for this value. And it turns out to be around, I didn't actually calculate this, turns out to be around 11 kilojoules per kilogram. At this point, we have our value for Y, we have all of the enthalpies, so we can solve for our work for the pumps in. Last but not least, theta is our net work divided by Q in. Net work turns out to be, when you perform the math, well, I'll do this. It's 1166 minus what I said was about 11 kilojoules per kilogram divided by Q in is 2613. Both the numerator and the denominator have units of kilojoule per kilogram, so we're left with dimensionless units, which is proper for our thermal efficiency. This turns out to be 44.2%, like so. And part C, which asks for Q out, this is actually pretty simple at this point. Q out, going back up to our diagram way at the beginning here, occurs only in one location. It occurs here at the condenser. So really all we need to determine is the mass flow rate, the enthalpy change across the inlet and the exit of our condenser, and factor in the mass flow rate passing through the condenser, because it's not the total mass flow rate, it's a percentage of the total mass flow rate. So to avoid any mistakes, you can always start with the first law. dE dt is equal to, you're sick of writing this, Q dot minus W dot plus M dot inlets. M dot inlets times the enthalpy at the inlet plus the summation over all the exits of M dot exit times the enthalpy at the exit. Condenser is in steady state. There's no work being performed on or by the condenser itself. Q dot turns out to be, well, M dot of all of the exits. What are the states at the exits? We go back up to our diagram. The exit is state 4. The inlet is state 3. So this will be equal to M dot 1 minus Y. The inlet, I've already forgotten what it was. The exit The inlet was state 3, the exit was state 4. H4 minus H3. Okay, so this value is going to be a negative quantity. So if we say Q, which is equal to Q dot over M dot, don't forget. So I bring the M dot over to the other side, and I call Q out positive, then I can swap H3 and H4 with one another, or just keep the absolute value of what I solve for. 1 minus Y, H3 minus H4. Q out turns out to be 1458.4 kilojoule per kilogram. I said that pretty quickly. Let me repeat myself. It's oftentimes it's a lot easier for us to study these cycles in terms of positive heat exchanges or positive work. Now, we've had a sign convention that dictates that heat added into your system is positive, heat leaving your system is negative, or the opposite is true for work. Work done by your system on the surroundings is positive, work received by your system from the surroundings is negative. But so that we don't confuse ourselves with the positive and negative signs, one way to make things a little bit easier on ourselves is just to define everything positive and then use words like in or out to describe the direction that the heat transfer is moving or the direction of the work. So work in received by the pumps is still a positive quantity because we say that it's work that's going into our system. By using the word in, that defines the direction of our arrow, and we don't have to worry about, oh, is it a negative sign or a positive sign, so on and so forth. So what happened here when we were solving for Q out, because generally we consider heat transfer out of our system as being a negative quantity, and that would have agreed with how we had originally set up the equation, m dot times 1 minus y times h4 minus h3. H4 is less than h3. This would have been a negative quantity. And we would have said, okay, well, that represents heat out of our system. I say, well, let's just keep everything positive and call Q out at this point a positive value. So that's what allowed me to switch these terms, H3 minus H4. Or you could have just determined using H4 minus H5 and then defined out and taken the absolute value, just switching the sign. Hopefully you found this useful. And please refer to it. Ask me any questions as you see fit.